the first method of determining apportionment in our textbook is Hamilton's method, and how our textbook flows in a very historical order, where it's examining the methods of apportionment as they were used in the U.S. House of Representatives. And I'm going to try to follow along with that storyline to help you see, well, why did these different methods develop, and what are the key mathematical differences behind them? But it was proposed by Alexander Hamilton in 1792, and they used it for a little while before they figured out, okay, actually, there's a little bit of an issue here. Um, and yes, and if you look up what is apportionment, the more general definition is giving out a bunch of objects to a bunch of different groups. But a lot of times, apportionment is, sometimes defined to be exactly what Hamilton did, is to give out seats to states, or basically trying to assign a number of representatives based on different populations of different states. But let's look at what is Hamilton's method and how did it work. Step one, calculate each state's standard quota. And so as we did before, that's the same kind of idea. Start with the standard divisor. That's always step one, really, is the standard divisor, because to find the standard quota, you need to take each population and divide by SD. Step two, round the standard quotas down and give each state its lower quota. So in the last example, we kind of looked at what's the issue with the lower quota, upper quota. But if we always give the lower quota, we're always going to be cutting off the decimals, basically giving out too few total seats. And what that will allow us to do is give out the remaining seats based on step three. So step three, give the surplus seats one at a time to the states with the largest residues, or what that just means is, what's the decimal remainder, what's the little portion of the decimal point left that was cut off by rounding until there are no more surplus seats. And we'll go ahead and do that in the example. Let's use Hamilton's method to determine the apportionment for Hamiltonia. So in the packet, there's an example, and let's just go ahead and work on it. And actually, let's say we were returning back to the example we were just working on for parking spaces. In that case, we had two surplus seats. So what Hamilton's method would say to do is give those surplus seats, which there's two of, to the states with the largest residues. So if we're looking at that, basically it's whoever had the largest decimal points. In order, we want to give those to the largest first, and basically give them one at a time. So if we're looking at this, the underclassmen had the largest residue, number one, so they would get the first surplus seat. Basically, they're going to increase from their lower quota to their upper quota instead. And then the staff had the next biggest with 0.58, right? And the other three are less. So basically, additionally, staff would get their upper quota 19. Basically, I'm adding one seat to each of those two with the largest residues. And once I've run out of my surplus seats, then that's it. Every other state will stay the same, or will remain at its lower quota. And notice that in that case, this is a proper apportionment method, because it's going to give out exactly the number we set to do. And that's the key with an apportionment method. Does it actually give out M to N? In this case, we're giving out exactly 100 seats to those five groups, or those five states. And this would be our answer. So this would be basically the Hamilton's method solution. And that's why it's a little bit more complicated than just doing some simple rounding. But basically, it's always following the steps: round down, give out the surplus in order. So let's work on a couple fresh examples. Let's start with example 2 from the packet. It says the following table lists the populations in millions of 6 states in Hamiltonia, a fictional nation. Let's say Hamiltonia has 250 seats in its House of Representatives. How many seats should each state get? So apparently state A of Hamiltonia has 1,646 people. Well, this is in millions, so this would be 1.6 billion people. State B has 6.9 billion people, so this is clearly not on Earth. State C has 154 million people. State D has 2 billion. State E has 685 million. And F has approximately 1 billion. So there's a whole lot of people, apparently. And if we want to know, well, how do I get going? How do I give out this many seats to each of these? How many should each group get? Well, it's always going to follow that same pattern. First step, find standard divisor. And if you want to think about mathematical formulas, the standard divisor is always P divided by M, which is the total number of people divided by the total number of objects. So in this case, step one is to find the total, which is something that you're not always going to be given in a lot of your problems. But so I need to take 1646 plus 6,000. Let me go ahead and type those all out. Hopefully I typed that in right. And it turns out that the total population of Hamiltonia is 11,018. But it's a fairly substantial amount. Let me just look at this and make sure I didn't mess it up. I did mess it up because I missed a 6 already. Okay, let me do that again. 1646. I think I typed too fast. Plus 2091. Trying to use the numpad here without looking at it. Okay, and so that number seems more right. And another thing is, like, how did I know that that number was off? Well, I've done this example a few times in my life, and I think I designed it so that the numbers came out a little bit nicer. But in the real world, the numbers wouldn't necessarily come out to be as nice and pretty as 12,500, or really 12.5 billion, in the context of this fictional problem. But anyways, the standard divisor is always the total number of people divided by the number of objects. Or in this case, there's 250 seats, and we're trying to divvy up those 250 to each of these groups. That's going to always be the denominator of our standard divisor, and that ratio should give us what we need. And if we go ahead and do that division, that would leave us with 50, which is the standard divisor. I'm going to go ahead and box that because that's like our key number. Also, why is it called a standard divisor? What does that name mean? Well, the term divisor means something that I divide by, or aka it's like a denominator. It's what am I dividing by? And since it's a standard divisor, it makes sense that we use this to divide for the standard quota. And kind of the name tells us how to use it, right? Because what we're going to do is take each population, divide by that, because it's a divisor, that's what a divisor means. And then that should give me my standard quota based on the standard divisor. And that's our next step. That's always step one, find the standard quota. That's done by dividing by the standard divisor. So 1646 divided by SD. Basically, I'm going to do that for each case. 6936 divided by 50. And I'll do 3 at a time so that I can copy the answers down as I'm going. So we got standard quota for A is 32.92. Standard quota for B is 138.72. Standard quota for C is 3.08. And continuing 2091, 685, and 988. And this would leave us with 41.82, 13.7, and 19.76. And again, I don't need to do this total because the sum of each of the standard quotas should always add up to the number of seats. And this is actually a little hint for your homework. Occasionally, your online homework will give you a question where they don't give you the populations, they only give you the standard quotas. But you can actually figure out a lot of the other information by the standard quota, because if you add these all together, this will always give you M, the sum of each of those. So if you're trying to figure out how many objects do I have, you can always do that by adding this up. And actually, if you add up the sum of all of these, that's 250. And then if you take 250 and multiply into each of those numbers, you can actually go back and reverse engineer the original population. Because if you think about what these numbers mean, really, this number was created by dividing by this number, the sum of them all. If you just multiply those two back together, you're going to return to the original population. Sorry, I said that wrong. You need to take each individual number and multiply by the standard divisor. So if you took the ratio of each of those two numbers, you could get the standard divisor, and then I could take 19.76 and multiply by 50 to get back to there. Sorry, I misstated what I meant there, and hopefully I was not being confusing, but I'm just trying to help. There is a tricky set of questions, and there's actually a slide later on in the lecture notes that has some hints for those types of problems. So if you get stuck on those, we can always talk about them in office hours or something. But just kind of warning you. Anyways, let's continue with Hamilton's method. I'm not trying to get off topic here. Okay, so what is the lower quota? Well, basically, I'm going to take each standard quota and round them down, regardless of what decimals remain. So rounding them all down would give us the lower quota. You always do need to figure out what's the sum of the lower quota, because step 3 is to take the surplus seats and give them out to the largest residues. And we can see the residues based on, well, what was the decimal point that was cut off? So I'm just going to go ahead and note that here. And we don't need to know the sum of the residues, but we do need to know the sum of the lower quotas. So 32 plus 138 plus 3 plus 41 plus 13 plus 19 would be 246. And of course, what I can see is that there's an issue with the lower quota is that it's 4 short of the actual goal, which is I have 250 representatives. I don't want to shortchange any of my states. And if we have that many seats, we usually want to make sure they're all filled. So basically, we have 4 to be given out, and we want to give them out to the states with the 4 largest residues. And looking back at each of the populations, we can go in order. Well, it appears as though A has the largest residue, then D, then F, then B. And in that order, what you could do is just circle which are the largest ones, and circle as many as you need. In this case, I need to circle 4 for surplus. And then to finish the Hamilton apportionment, we start with the lower quota. Each state that had the highest residues gets one of those surplus. Basically, we add 1 to each of the ones I circled, and the other ones are going to stay the same because they did not have large enough residue to give them out. And that should apportion exactly 250 seats because I started with 4 too few, and if I give out exactly that many, I'm going to have exactly 250. So that's the beauty of Hamilton's method. It's a fairly simple way of dealing with the issue of division, and it always works just by rounding down and giving out how many are left. We'll do another example in the next video, and we'll also talk about some issues that arise when using Hamilton's method of apportionment.